another example. All right, a little more real world, and I think at the end we get to a really good real world problem at the end of it. So let G equal the taking a math class, the event of taking a math class, and let H be the event of taking a science class. So these are people, right? Taking math classes we're talking about here, people taking science classes. And randomly choosing, we're talking about the probability of randomly choosing those people that are taking science or math classes. So what's the probability I randomly choose somebody and they're taking a math class in here? Well, 100% because you're all taking my class. So, unless we count this as a statistic course, which I guess it is. So, all right. So, we have some probabilities here. So we know essentially some things about our college and who takes what. So the probability of G, for instance, probability G, which is taking a math class, is 0.6. So, right, the probability that I randomly choose somebody from my college, right, and they're taking a math class is 60%. That's what we're saying.
Pretty high.
Yeah, pretty high. Because math rocks. So, the probability that somebody is taking a science class is, 50%. The probability that somebody is taking a math and a science class at the same time is about 30%. So we can say, right, it doesn't look like we talked about it here, but are these events mutually exclusive? What tells us that they're not mutually exclusive?
G and H.
That probability is not 0, so they're not mutually exclusive. So just pointing out. So not 0, not equal to 0, so not ME. One does not exclude, right? And that makes sense too, right? Just because you're taking a math class doesn't excuse you from taking a science class.
Right.
Or vice versa. So the real question is, are they independent? So we can test out in one of these 3 ways. Typically not so much this way. I've never actually used that, but I don't know. I'm using the new book, so maybe there'll be requirements from this new book that we need that. So probably shouldn't have crossed that out, but there it is. I crossed it out. So we can use one of those 2 things on the top to try and determine if this is independent or not. So let's talk about that. So we do have a formula, right, that allows us to find something like the probability of G given H. Remember that formula? P of G and H all over P of what? P of H. Because H is in the bottom, so H is in the bottom there. Doesn't matter how you write that top one. This order doesn't matter up there. So do we have these 2 probabilities in our above statement?
Yes.
So probability of G and H is 0.3. And then probability of H is 0.5. If we divide those, they get 0.6. What the heck does that tell me?
It's not
I don't
mutually
know.
exclusive.
I agree with that statement, Taylor.
But
I don't know. So this, right, we want to prove that this equals P of G or not, right? So vice versa. So is this thing we just found, which is 0.6, is that equal to, what do I want it to be equal to?
P of G.
P of G. So P of G is equal to 0.6 as well. Just given to us. So P of G given H, I'm just going to write this down, is equal to P of G. So
Yes.
yes, it is. It is. They are, I should say. Use correct English because there's a couple things there, Andre. So they are independent. So, and as a college, we can test this out to see if there's a dependency between two programs. One's dependent on the other. So this would be maybe a common example that we could use at college to see if there's a dependency between science and math. I would think actually it would come out to be. So
Me too.
I don't think this is necessarily a real world problem, but I would think there would be some dependency, right, on this, because many people who take science classes have to take math classes together. So I would think it would show some kind of dependency if we had those real probabilities. All right. So we can check for independence in a few ways. So let's move on. Example 6. Let event C equal taken in English class. So similar idea. Let event D equal taken a speech class. So they're not mutually exclusive. Oh, I shouldn't say that. We're going to answer that question. So here's the probabilities. Maybe they are.
No,
Let's find out.
they are not.
I would say they're not, right? Not thinking about the ideas of taking a speech class versus an English class, right? We can definitely have somebody in here that is taking both at the same time. There's no harm in that kind of thing. So one does not exclude the other one from happening in this case. So I think that they aren't mutually exclusive, but let's play around with the probabilities and see what the probabilities tell us, because that's what I want you to do on your test, right? So if I'm looking for are C and D independent, right? I have the probability C, the probability of D, right? And I have the probability of C given D. So since I have this probability, right, which goes into independence, this given condition, I want to compare this to which one, C or D, the probability of C or D.
See,
Oops, I'm really low, I apologize. I just realized where my notes are. Finally looked up. So probability, what do I want to compare this to?
P over D, or P of D, sorry.
C, P of C, right? If it doesn't matter whether D occurred or not, right, this will equal P of C. That's what independence says. Right? So independence says, doesn't matter that D occurred, I have the same probability, the same outcome. So if these two are equal, then we have independent events. What are these two? This is 0.75, so we're asking this question. We got 0.75, C, P of C is also 0.75, right? There's P of C, there's P of C given D. They are the same. So they are independent. Let me put a little check here. Check. So they are independent. I wrote way too big for this. I got other parts to do, Andre. So I'm just trying to say what's happening here. So I'm checking one of my conditions. Do you understand this statement? Why I got this statement? Right, so the conditions for, let me move this down. I'm going to move this down for a second, I'll move it back up. Whoop. All right, so these are the conditions for independence. We can check them. All right, so I'm just checking them to see if it works or not. If it works, then they're independent. If it doesn't work, if they're not true, if it's not true, that they're equal, then it's dependent. Change, something changed about, right, the probability. There's a given condition change.
So if it's not true.
If it's not true, it's dependent. Because something changed, the given statement changed the probability, changed the outcome of that happening.
So it equals PC, is it because C can
No. Oh, yeah. So, right, so notice, right, this is
Right.
for, right, so what these are saying is essentially you got G in the top, G here, right, H in the top, H here. Right. So opposite of that formula we were using before. So here I got C in the top, so I'm going to make sure C's over here. If I compare it to P of D, then it's going to look like it's dependent, but that doesn't tell me anything, technically. So they are independent for this reason, because we checked it and it worked out. The check worked, so they are independent. Let's talk about mutually exclusive. How do I tell two things are mutually exclusive? POC,
Equal to 0.
yeah, POC and D equals 2.225. Is that 0? No. So they are, that's supposed to be a they right here. Oops, they are.
Oh, they are.
They are not, sorry. They are not mutually exclusive. Checking for independence versus mutually exclusive. It's a little test. So taking a speech class is independent of taking an English class. There's no dependency, which kind of, to me, makes sense. You might be taking a speech class and an English class at the same time, right? On purpose. Okay. So they usually don't go hand in hand. So last question on this problem. What is the probability of
What is
P of D given C, which we can calculate using the probability of D and C over the probability of C? Thank you. What's the probability of D and C? It's the same as C and D. Probability of C and D is given to us is 0.225. Zero 0.225, yeah. And then the probability of C is 0.75. If I divide those, I have no clue. 0.3, thank you. Oh, no, 0.3 you said, not 0.03. 0.3 like this. 30% chance that somebody is taking a speech class given that they are already taking an English class. So we know they're already taking an English class. We're asking what is the probability that they're also taking a speech class. That's about 30% in this class. Yeah.
Why would it be 0.225 when that's what C and D is, not B and C?
Yeah.
It's the same thing. Doesn't matter which way you order those two things, the sets are going to be the same. Whether you're talking about C and D versus B and C.
And why did it give you the P, D over there as 0.3?
P of D. Yeah, we didn't use it in any of these things. I think they just gave it there to try and cause some debate. Because I think we were talking about this condition, right? And I think a lot of us wanted to write P of D up there, but it has to be C because the first one is C. So this has to be C.
And that is
That is a
because I'm
difference.
thinking, that's supposed to be blowing me away.
You're not used to my writing by now?
I'm like, what is PCC?
That's a parenthesis. You weren't the only one, Jewel. I don't know what you're talking about. I don't know why my students are so confused all the time. I wonder. You see, like other people are like, what? That was a C.
So stuck. Okay.
So for C, the probability of taking speech class and English class is 30%. Is that what?
No, so the probability of taking a speech class and a English class is actually 22.5%.
So what is the
So this is probability of taking a speech class, somebody taking a speech class, given that we already know they're taking an English class. So we already know they're taking an English class. So it brings my group down, right? Not everybody's taking an English class, right? Where this set, right, is out of everybody. Includes people not taking English, not taking speech. Well, they have to be taking both English and speech. But right? The overall group, the denominator, is out of everybody that we're talking about. Whereas this changes the denominator to something else. Because we already know they're taking English, so what's the probability that they're taking speech as well? Different group?
And then you said good thing.
Yeah.
So C.
So this doesn't tell us
Oh, that
anything
has-
really about
okay, you're
independent or
right.
dependency.
It's the.
Well, actually, sorry, this is P of D, right?
Okay.
So we could determine that they are independent as well
Okay.
with this method.
We already
right?
did though.
Okay.
Yeah, we already did it with P of C given D,
I like that
right?
one. It's
Is equal to P of C. But this is also, right, if this is equal to P of D, which it is, that's also another way to show that they're independent as
Right.
well. But I don't want to go there. Just pointing out they're equal.
Coming to A, does it matter if we say like, instead of P, C given D, because, possibility of C. So instead of like P, possibility of C given D, when you say P, D given C,
You could have, but here's the problem, we had to calculate it. What was given to me, I was given, can't reach all the way up there. I was given, right, this one. I wasn't given the other one. I had to find it. Since I was given this one, I'm gonna use that one. Yeah, and so I have to compare this to P of C, because I don't have the P of D given. All right. One more example. No, this isn't, no, two more examples. Three more examples? How many more examples? Oh, two.
Try it.
That's a try it. You can try that. What time is it?
It's 32.
Thank you. 20 minutes. Thank you. All right, so a different kind of card game, so we can understand it a little better. I think it's in 3.3 where I have a good real world problem. And yeah, in 3.3 I do have a good real world problem to talk about things. So, all right, so in a box there are 3 red cards and 5 blue cards. 3 red cards are marked with the numbers 1, 2, 3, and 3 blue cards are marked with the numbers 1, 2, 3, 4, and 5. So the cards are well shuffled. You reach into the box, you cannot see into it, so we're assuming it's randomly chosen kind of thing. That's all it's saying. Draw 1 card kind of thing. So here is, right, so kind of some extra stuff, even numbered cards, blue cards, red cards, right? If I want a red card, so here's my sample space. This should have like little squiggly brackets around this space. All right, but we got the notation here. I got a red card that's with a 1, right? Red card 2, red card 3, 4, right? Label like that. So these are my possibilities. That's my sample space. I have how many cards?
8.
8. It says it, huh? 8 cards.
Yes.
So, what is the probability that I choose a red card? 3 out of 8. Probability of a blue card? 1, 2, 3, 4, 5 out of 8. Probability of a red and a blue card? 0. Nice catch, right? Confusing word, right? It can't be red and blue. No, that's purple, right? We don't have purple cards.
Right.
So, I wouldn't do that to you either. Switch it up, give you a purple card, and you're like, wait, what? I gotta do that too. All right, so it's 0. There's no possibility of mixing this up and having a red and blue card at the same time. So the probability of getting an even numbered card. So even. So let me use colors. Even card. There's a red even. There's a blue even. Another blue even. I got how many evens? 3 out of 8. So now we're given their blue card. We're given their blue card. So I'm going to do something up here. You're looking at the sample space. We're given their blue card. I'm covering up all the red cards. This is my new sample space. I have how many cards in my new sample space? 5. It's like taking out, I'm literally taking out all the red cards out of this hat or whatever we got in it. right? So this is my new sample space. How many even cards do I have in this space? 2. So I have 2 out of 5 total. All right, you see the 2 orange there?
Yeah.
Out of a total of 5 that I left uncovered. We literally took those red cards out, so I don't have them. Right. So now putting them back in, right? Now I'm really taking out, what am I taking out here? This is so we're given the even.